great pleasure for me to speak to young people. So particularly for somebody coming from a century ago, I started my research in the 20th century. And at that time, the main paradigm of research was divide and conquer. So here you have Ilya Prigogine, who was a Nobel Prize in chemistry, who said that from the historical point of view, the idea was that the great success of science consisted in breaking down systems into pieces, into atoms, into molecules, into elementary particles, into biomolecules, into individuals. So I use it to pleasure. I use it to joke to my students and say, okay, I remember somebody was coming and say, I'm interested in life, but the life is too complicated. So let's go to start the individual. But you know, individual is very complicated. Let's go to study the cell. But the cell is too complicated. Let's go to study DNA. But DNA was too complicated. Let's go to study DNA bases. But this is too complicated. Let's go to study atoms. And at the end of the day, say what the hell I was trying to understand. Because he was splitting so much the problem that as our grand genius of the Spanish science, Santiago Ramón y Cajal, wrote in a book, which I recommend very much to young people, is say that we are far from condemning the excellence of the division of labor. So it is okay to divide problems into parts, but let us agree that the excessive fragmentation of scientific work entails certain disadvantages. One of these consisted in separating the inseparable, that is, in locating the term of the same reasoning under different heads. So if you try to understand a problem with the ideas of the 20th century, you need a whole bunch of scientists from different disciplines to understand one particular problem. So when I started in research, and this is my statement 0 of this talk, I was really interested in a theory of everything. Okay, now if you look at what is a theory of everything, you will see, for instance, what Michio Kaku, that you can surely watch him at the TV and say, well, this is the God equation. This is another book, The Quest of Everything, the quest to explain all reality. And here you have another, the theory of everything, and says that quantum mechanics and gravity are everywhere. So I don't know where to look at this book, if in the section of science or in religion and mythology. But the real thing is that I am not a physicist, so I cannot complain about these things. But let me take what the proper physicist says. And not any physicist, but Robert Rödlin, that was a Nobel Prize in 1998 by the study of particle physics, and David Pines, that was the Dirac Medal, among other prize and distinctions. They say that predicting protein functionality or the behavior of the human brain from these equations is patently absurd. So the triumph of the reductionism of the Greek is a Pyrrhic victory. We have succeeded in reducing all the ordinary physical behavior to a simple, correct theory of everything, only to discover that it has revealed exactly nothing about many things of great importance. So then I changed, okay, to another statement, and I call this my statement 1. So I am interested in some theories of almost everything else. And what I mean, okay, I'm interested in systems at the big scale. Let's say not at the universe, but it could be, but at least at the level of interaction between countries, nations. And then if I pick one of these regions here, I can try to understand the whole bunch of interactions between different species, including ourselves, in this ecosystem. And then if I pick one of these species here, let's say that I pick the humans, I can also try to understand what is the phenomenology and the characteristic of this human scale. But then I can take an individual, and then I can analyze at a physiological scale what is happening in the interrelation between the different organs, circadian clocks that exist in the different organs, the metabolism in which all of these organs are participating, and so forth. Or I can pick one small, tiny piece of any of these organs, and try to understand the histological scale, how the cells interact to each other, how they are organized, what happens when there is a malfunctionality of these cells, like in a cancer, for instance. Well, then I can look inside at one of these cells. And at this cellular scale, and this is very funny, because if you take the textbook picture of a cell, it's very empty. It is like, okay, so this is the nucleus, here you have the back wall, and here you have the organelles, and blah, blah, blah. This is very far from real. This is a reconstruction by using electron microscopy of how the internal part of a cell looks like. There are 40 million proteins inside. So it's a very, very crowded environment. And these condition the way in which chemistry and physics and biology take place inside. So not only diffusive processes are there, but there are anomalous diffusion very commonly in these cellular scales. But then I can pick one of these macromolecules and try to understand these at the atomic scale. And what I'm going to show you today is how I have been traveling across all of these. Unfortunately, because of the lack of time, I cannot show of all of the scales, but I have examples of my research in any of these scales. So in my personal experience, and then this is the only statement I am not proving mathematically in this talk, but I will show you some examples, and no one can give me a counterexample of these. I have found only one mathematical theory that can embrace all of these scales, and this is network theory. And this is not proper propaganda about network theory, but it's just like I say, okay, so what I am seeing is that I can use integrals and derivation or calculus in general in most of the continuous space analysis that I can do. Well, because all the complex systems are discrete systems, the only way that you have to study these, represent this, is by using network theoretic kind of tools. So then these are simple graphs, not simple graphs, they are graphs representing the main skeleton of the complex system. I have realized that you all know a little bit about network theory. Is somebody that has never been approached to networks? Could you please raise your hand? And then I will spell from it now. Okay, so then if, because there are some of you that not, so let me introduce what is a graph. Graph is the simple mathematical object that you can imagine. It's just a pair of sets. And then I remember when I was doing applications in chemistry, there was always a chemist raising his hand and saying, okay, it is well known that the properties of a molecule depends on the three-dimensional structure, and you are considering a two-dimensional object. And I say, no, my friend, it's even worse. I am considering a one-dimensional object because I only need the set of vertices and a Cartesian product of this set onto itself. So it means that I am not in two dimensions, I am properly in one dimension. But if what you are trying to capture is just the connectivity of the elements, how things are connected to each other and how things depends on this connectivity, then this is a very good approach for this particular case. So I will use n always for number of vertices and n for the number of edges. A good representation of this that contains all the information you need for the topology of the system is by using the adjacency metric. This is, in the case that there is no directionality, is a square symmetric matrix. In case that there are directions, it is a non-symmetric matrix. In the case that you have weights, so you replace these ones here that represent the connectivity between a pair of vertices by the corresponding weight. And this weight could be whatever you like, okay? Number of emails, so this is an integer, but it could be the flow of particles between two positions, so that's a real number. But if you are a quantum mechanics, you can put there a complex number, okay? So there is no limitation for what you can do here. So any square matrix represents a graph. That's my best statement of today. So any square matrix that you have, you can do things by using a graph. There is, basically, we typically use algebraic properties to understand graphs. But there are people like Richard Roaldi, for instance, that has made all the career by taking properties from the graph to understand the linear algebra. So this connectivity between the two fields is in both directions. So here you have more or less resume. So if you have entries in the main diagonal, which we call self-loops, this represent, for instance, species that eat to themselves, possibly one over here, or genes that self-activate, etc. If you have ones here, it means that this node is connected to this other node here. If this is not symmetric, it means that there is a directionality between this node to this, but not in the other way around, and these kind of things. You can have a look at most of these concepts in this book that I published a few years ago by Oxford University Press. So one very important operator that we are going to use in most of my talk is the Laplacian operator. You all have studied physics, so you are very tired of hearing about the Laplacian. So in the heat equation, in the diffusion equation, in the Schrödinger equation, and blah, blah, blah. So here we also have a Laplacian operator. And in the same way that the Laplacian operator is an operator in a Hilbert space, our operator is also an operator in a Hilbert space. So I can define this function operating on the set of vertices which are in my network, and this function could be, again, in the complex field, or it could be in the real field, or in any field that you like. And this operator applied to this function over the set of vertices, what it do is taking the difference between this function applied to the node that I am considering and all the nearest neighbors that I have. If you want to reconnect this with the heat equation, you can consider that when you apply the heat equation in the discrete setting, what is happening is a consensus or agreement process between the temperature of one region and the temperature of all the nearest neighbors of that particular region. And this is controlled by this operator here, as I said before, is just in the L2 Hilbert space defined on the set of vertices. So let me go quickly here, because what you have is that in this particular operator, when you have a discrete network, which is most of the cases that we are going to analyze, but not all, you have the degree of the nodes in the main diagonal, which is just the number of vertices which are adjacent to one particular vertex. In other words, it's the number of edges which are connected to one particular node. And outside the diagonal, you have -1 if the two vertices are connected, or 0 otherwise. So it's a very simple representation, but what it's doing is exactly what I was telling you before. So let's go to the first example. Let's go to an example in the global scale. And to talk about the global scale, I have taken something which is rubbish, as the British says. It's garbage, is waste. So it's the worldwide waste web. Is the web of international trade of waste materials or hazardous waste in particular between the different countries. So let me start by defining what I mean by the worldwide waste web. So this is a network which is directed, so there is not necessarily the same connection between A and B than from B to C, and it's weight. So it means that there is a weight over every of these edges here. And this weight comes from the amount of hazardous waste which has been exported by this country to the second one among 108 categories that has been classified by the Basel Convention. And the Basel Convention is the UN Organization for Controlling Transboundary Movement of Hazardous Waste and Disposal. So in this way, you can have that the nodes of these networks are the different countries in the world that, of course, report to the Basel Convention. Otherwise, you cannot have information about them. And then you have one directed line from A to B with the amount of waste that A export to B, and then another line connecting B to A with the amount of waste exported from B to A. But things are not so simple. So look at this data here. So this is the amount of waste that countries has traded legally in the period 2001-2019. So this is about 1.5 billion in English, or 1,500 millions in the case of Spanish, millardos, during this period. So this is 4,000 times more than the weight of the Empire State Building. So it's a huge amount of waste. But this waste traded represents only 10% of all the waste that we produce. 10%. So among these waste, which are 108 different categories, for modeling perspective, this is a nightmare. So we have made a reclassification of this waste into 7 categories. So grouping together in such a way that, for instance, we have the type 1 waste, in which we group all the clinical waste from medical care in hospital, medical centers in clinic, waste from the production of preparation, pharmaceutical, biopharmaceutical, and also agricultural industry, residues from industrial waste disposal, etc. And this represents 54% of the waste traded by the worldwide waste web. 36% corresponds to the most dangerous of the categories. So these are the category that contains 27 chemical elements, particularly heavy metals, not the, the heavy metals like lead and chromium and things like that. And most of the e-waste, your fridge, your TV set, all of this goes into this category because all of these contains a huge number of chemical elements, 50-something chemical elements contained in this material. So this category is mainly dominated by e-waste. And here you have the household waste and the incineration products of the household waste. And yes, here we have almost no problem with this, but there are countries like Senegal that has to export their own household waste because it is covering most of the landscape in the country, in the streets, etc. of that particular country. But here are the problems. So we spent 6 months just to download and clean all the data from the Basel Convention. So in the Basel Convention, you have this type of reports. So this is the export reports and the import reports. It means that every country voluntarily report how much of one particular waste export to another country, and the other country report how much waste it has import of this particular type of waste from this other country. You will figure out that these numbers coincide. No, they almost never coincide. So waste apparently is created and destroyed during the trade. So sometimes it happens that A reports exporting 100 tons to B, but B reports it imports 80 tons of the same waste from A. What is happening? You can speculate. Okay, you can speculate. There is no information at all about that. It could be that some of the waste was retained in one of the intermediate points, that some of this waste was disposed in a third world country or elsewhere in the sea, etc., etc. So in order to manage with this nightmare of data, we have done the following. We have integrated the system trying to capture the worst case scenario. So it means that I will take the maximum amount between the one reported as exported and the one reported as imported, and then taking this as the way of exported from A to B. So we have either 100 or 80. So I decided to take here 100, which is the maximum one. So then I will have a weighted adjacency metric, and I can normalize this weighted adjacency metric in order to have numbers which are manageable. So what we did is just simply divided by the total sum of the waste. So the total amount of waste that has been traded during this year. We start at the January of every year, ends in December, start again in January the next year, and so forth. So now we have that due to this asymmetry in the data, in order to capture the true possibilities, we split our model into 2 particular types of problem. So a country can be congested by the arrival of waste from abroad, or it can be congested by the departure of waste from this particular country out. So this is trying to capture those countries that already has a problem of waste in them, and then their problem is that they need to export this amount to abroad, like the case I mentioned of Senegal, that exported 1,500 tons of household waste to Italy in, don't remember, 2000 and something. And this is then made by these two different types of models. So what is the problem that we want to model here? So what we want to model is to consider that the country I can be either susceptible to get congested, or it is already congested of a waste of a given type at a time t. So it is a sort of susceptible infected kind of logistic equation in which what you will have is that at the beginning of the time, from the period of January to December, the waste amount or the probability of getting congested of this particular waste increase exponentially until it arrives to a saturation point. And at this saturation point, we have that the capacity of this country for processing this type of waste has been reached. But we cannot know what are these capacities of processing the waste for every single country, and it depends very much on the country that you are studying. So what we do is simply take a worst case scenario that I'm going to show immediately in the math part of the work. But another thing that we have to take into account is that there are time delays. So the amount of waste that is imported by a country coming from another country is not departing immediately from that country to this, and once it arrives to this country, is not disposed immediately at this country. But there are part of collecting this inside the country, packaging it, waiting in the port of this country, etc. So we still don't know what are these time delays for any type of these waste. So there are many unknowns that we have to try to sort out by using the mathematical model. And here is the mathematical model. So first of all, this OB equation here is just a modification of the logistic model in a way that we have transformed it to consider, first of all, an upper bound. So we have proof analytically that this equation, the solution, represents an upper bound for this, and also is linear. But you know from kindergarten what happens if you linearize the logistic equation. Oh, divergence. So then we have to guarantee that our linearization is not exploding, but that it converges to the probability 1 as it should be, but always with the probability of getting congested, which is larger than the real susceptible congested model. And the second part is given by this, which tries to capture this time delay. So this time delay is captured by changing the normal first derivative that you use in the susceptible infected model by a fractional derivative. What is a fractional derivative? Okay, you know the first derivative for something, the second derivative for something, the third derivative for something. What happens if I take the 1.5 derivative for something, the 0.3 derivative for something, the Euler derivative for something? Well, this is well defined, and it's not new. It's from Newton's and Leibniz times. Okay, almost immediately after the invention of calculus, the hospital asked, what happened if I take this fractional derivative? And then people started to create models. And one of the most physically appealing models has been developed by Caputo, which is an engineer, Italian engineer, still around. And this is the kind of derivative, and I will show you the definition immediately, that we have here. So this model here is just a linearization, so forget about all this stuff here, but this is just a linearization of the SI model in which I have replaced the normal derivative by a fractional derivative. And this fractional derivative is not other thing that an integral differential equation. So there is a natural way of defining this derivative by taking this integral differential equation. And recently, in a paper in New Journal of Physics, I don't remember in which one, I make an interpretation of this derivative as a time delay that is taking into account the history of a process before the process takes place at the time t. So what is important here is that the solution of this model is very simple. This is just a linear equation in which this here is a generalization of the exponential. Remember what is the solution of the logistic model? It's just the exponential of time here and the adjacent symmetric in the case of the SI applied to a network. Well, here that we have is the Mittag-Leffler function, which is just a generalization of the exponential. If you remember that the exponential is just taking the powers of the function, in this case of the metric, divided by the factorial. Then I can generalize the factorial by the gamma function, which are defined in this way. And these generalizations are always converging independently of the value of k, and for alpha strictly between 0 and 1. And then if you take here 1 for alpha, you recover the exponential. But then you have hyperbolic cosine, you have error functions, and you have other things that you cannot write down, like these formulas. So now we have to quantify the risk of congestion. So for quantifying the risk of congestion, what I say is that if I have these three countries here, which are trading waste, the first one that arrive at a congestion of the 50% of its capacities is the one with the highest risk of the three. So then it means that if I take the time at which 50% of the, so the probability of being congested, if 50% at this time would be the risk. So in this particular scenario, C, which is this dot line here, which is this node, is the one at the highest risk of congestion at arrival. But if we do the same for the departure, we can see a different picture. We can see that then the highest risk is the node A. It's a different country. So then this start to be like a lot of different results, and you start to get lost in understanding what is happening. So let's go to track to put everything into a single pot and defining a single index of the risk of congestion by taking into account both the congestion at arrival and the congestion at departure. So this index is given here, and this number here could be the minimum between the time at which the node I is congested at arrival or at departure. So then it means that if I have the same situation, but in this case for the node A, so I will have that this time for congestion of the node A at departure is smaller than this one. So then it means that the minimum of these two values is TDA. And then if I take the maximum of all the values of the two plots, I immediately figure out that this is just this time of congestion for the node C at departure. So then it means that I can obtain the risk at which the node A is for congestion by taking the combination of this information from both plots. But what could happen here? This is from the simulations. So this is a country like Burkina Faso. These are not snobist pictures taken for impressing you. These are pictures taken from scientific papers of the real situation produced by waste mismanagement in Burkina Faso. And of course, all of you have gone to Netherlands and you see this. How is possible that both countries are told by the model that they are at the same level of risk of congestion? Well, this index is taking into account that if you're a small country and you receive a lot of waste, you can be congested. It's not telling you if you have the capacity for processing this waste during a period of year. You are not taking into account the environmental risk that every of these countries is at during that particular year. And this environmental risk is an index produced by University of Yale and Columbia and take into account many of the environmental impacts that a country can do during a year. So if we take this particular information and put it here, what we will see is that both of them have exactly the same risk of congestion, but one of them, which is Burkina Faso, is at the very high risk of environmental pollution, and the other is at the very low one. So in this corner here, what I will have are those countries which are globally at a high risk of waste congestion and of poor environmental risk. So it means if a country is saturated of waste in the month of March, it can do two things: treat correctly this waste or expel producing environmental pollution. And this is what it's trying to capture. Of course, you have here in the middle certain kind of tolerance. Okay, for me, tolerance zone would be a line and nobody could be in the line. But we should not be so critical, so we have a subjective kind of tolerance zone. Okay, so of course, if you put this tolerance zone very wide, there are only one or two countries which are at high risk. If you put it very narrow, the number of countries at high risk would be larger. It depends on the kind of message that you want to give. Here are countries which are at very low risk, simply because they have very good track record of environmental protection, and they are receiving smaller amounts of waste than the ones that they can manage at the current situation. So they represent, in reality, investment opportunities for green technologies in those countries which already have a track record of good environmental protection. Let's go to the real world data. So we have the waste of type 1. So in this particular case, we have all the waste produced by hospitals. These are pictures taken from the scientific literature. There is a case in India of 60 people that died because they were using needles and informally recycled medical equipments, and they passed away because of hepatitis B. So it means that if these wastes are incorrectly disposed, incorrectly or informally recycled, there could be immediate health problems into the population. So here what we have is that for this type of waste, we have, well, most of the European countries are here. The colors are by continent. I think the blue is America, green is Asia. So this one is Australia, and so I don't remember. Okay, so here is, okay, so here are the countries in pink are the European countries. So most of them for this particular case, according to the data they report, are in the tolerance zone. But there are a few countries which are at a high risk of producing environmental problems due to this type of waste. The same you can do for the second type of waste, and the same for the third type of waste. See here, Senegal, that we already know by the news that it has this problem with the household type of waste, appear with a very high level of risk in this particular category. Now, what we can do is to try to match the different type of waste. Now, these are the 108 different categories produced by the Basel Convention, and certain kind of chemical fingerprints which are left and we can trace by the impact of this particular waste. And we concentrate here into three big groups. And this took a long, long time of being processed. So these are the volatile organic compounds like methane or small hydrocarbons, etc. These are persistent organic pollutants like polychlorinated biphenyls polycyclic aromatic compounds, etc. And here the heavy metals. And here we have the different countries. So we have now that, for instance, China can have an impact from the 3 different types of fingerprints coming from the waste which are disposed and informally processed in their country, and the same for any other of the countries in the list. Finally, we were interested, and our analysis was for a time series coming from 2001 to 2009, and see how these 2 indices of environmental underperformance or waste congestion risk has progressed during the time. So in this corner here, what we have are the countries that has deteriorated both indices in time. And here we have the countries that has improved both indices in time. No comment. So in this experiment, what we have done is, first of all, trying to put in the scientific literature a problem which is in the press, is in the news, but it's not in the scientific literature. And then we have tried to do our best in collecting the data, something that has been terribly hard. This has been thanks to one of the co-authors, Sergi Romero, who was in the IFISC, is not now anymore. And he did a titanic job in collecting this data. And the second thing is that you can adapt well-known mathematical equations in order to consider particularly new kind of problems that you can tackle. So I think I still have time. So let me send you another postcard. And this postcard comes from the human scale. So in this particular scenario, I will not talk about social networks, but I will talk about a problem that almost everybody here has confronted at least once in their life. It's traffic jams. So there is a very nice review here by these authors in 2010 about how to model these traffic jams in general. So why I was interested in this? So I received once an email from somebody from Iran. And he said that he wants to be interested in doing some research with a measure that I have produced, which is known as communicability. And then I say, okay, but you know, I am tired of theory and proving theorems and things like that. Do you have data? And the guy say, yes, I have the number of cars per hour at rush hour in my city during a period of time of a month. And I say, oh, that's fantastic. What can we do? And I say, well, we can model this, and then we can, you know, figure out how the traffic is moving in the city. His city is Isfahan. It has about 2 million inhabitants, so it's a city interesting to model. I am living in a town of 2,000 inhabitants, and normally there are 5 or 10 there. So then my idea was the following. Okay, so let's show to this, to the mayor of Isfahan, that most of people, because they have GPS and they have maps and they know the city, they go by the shortest path connecting every pairs of single areas in the city. Then this shortest path will be congested. So let's say, okay, if you take this other that we call communicability path, I will show you what exactly it is, you alleviate the traffic from this, and people will be more happy, and maybe I will receive a medal from the mayor and, you know, a party and things like that. But as you will see, the story ends in a different way. So first of all, let me remind you what is the shortest path. So a path is a sequence of absolutely different nodes or vertices and edges that connect 2 nodes in the network. So remember that a walk is a different concept. Most of physicists confuse this in the papers, but a walk is just a sequence of not necessarily different nodes and edges. So it can be backtracking. In a walk, can be backtracking. In the path, there is no backtracking. So the length of the path is the number of edges in the path. So the path with the minimum number of edges is the shortest path. And you can prove that this is a distance. It's a proper metric that fulfills the 4 axioms of a distance. Okay, so here you have. So this is just a random geometric graph, and this is the shortest path connecting these two randomly selected points. Now, because we have the data, we took about 20,000 randomly selected pairs of points in the city. We measured the shortest path and the length, the geographic length of the path. So what is the geographic length of the path? It's the sum of the length in meters of all the streets in that path. So if you go from here to there, you measure this one. And we are respecting the traffic. So the traffic direction, of course. So we immediately see that most of the traffic goes by the shortest path and not by the shortest geographic path. So people prefer in Isfahan, okay, in Isfahan, to go by the least number of streets, even if they are longer. Okay? Do you have any complaint? Go to the mayor of Isfahan, not to me. Now, that's more or less rational, because in one particular street, you can accelerate your car. But if you go to Milton Keynes, in which you have more roundabouts than whatever in the world, you cannot accelerate your car. You can, then you stop. So you have many intersections. You probably, this is rush hour, okay? Morning going to job, afternoon returning home. So you try to go as faster as possible. So this is very reasonable kind of result. But what happened to the shortest path? So you can prove that the shortest path between every pair of nodes with high probability contains the hubs of the network. Okay, so if you have a shortest path, if you have a hub, there are many shortest paths converging to this hub. So then the probability that you have hubs in the shortest path is very large. So if I go to this place, I think that this is in America, I don't know, so I just stop the car here and go walking. I don't know what to do. So here there are 8 different possibilities of going. So it is like a very large hub for a city. So then our model considered that at rush hour, if you go to an intersection that has as many lanes to go like this one, you will have to be with a waiting time relatively large. Remember, you can arrive here and there is a traffic line. First, this one has to go, then this has to go, then this has to go, and so forth. So if you go to one intersection in which you only have one street crossing, so the time that you have to wait there is relatively short. So then the waiting time here is proportional to the number of lanes that you have, like in the case of a random walker, with a delay time or a waiting time that you will have here to wait due to this particular scenario. So what we did here is just to take the normal diffusion equation in which instead of the Laplacian, we sum this delay time, and we don't know the delay time for all the intersections, so we put this as a constant for all the intersections in a city. So if you solve this, immediately you go to this expression here that ends up that the probability of getting congested at the time t depends or is proportional to the exponential of the okay, so this is t and this is a. Possibly you don't see it looks like q. So this is just the exponential of the yrCSS metric. And this is what we call the communicability of an error. In this paper that we published in Nature Human Behavior in 2018, we make a different derivation here. So we start from the equation of traffic flow of Lighthill, Whitman, and Richards, and then we solve analytically this into the Berger's equation. We apply a transform for that, we recover the diffusion equation, and then we prove that exactly the same solution that we had before. Okay, so now what I would say is, okay, so I am interested in seeing the difference between these two parameters. So here, GPQ is just the term in which I have the exponential of a set of parameters here, which include the time multiplied by the yrCSS metric. And this, you will see later, is related to all the possible walks going from P to Q, giving more weight to the shorter than to the longer walks. Walks, no path, okay? You can do backtracking here. And then what I go to do is to take this difference here. And this difference is just Euclidean distance between the nodes P and the node Q. So what we are doing is producing an embedding of the network into certain Euclidean space. And this certain Euclidean space is an n-dimensional Euclidean sphere. So we have proved that as well. But what is important is what this means here. So this is the capacity that one intersection has of being returned to it if you were a random walker. Suppose that you are a random walker, you arrive at one particular intersection, you don't know how to go, then you turn again, and then you find out exactly the same intersection. So let me tell you one thing that happens to me this morning. I was coming from the university to here by taking the metro. So I took the metro, I was thinking, and then after a very long time for my perception, I arrived at the university. So how is possible? I started at the university and then I finished at the university. I went down and complained, and the lady said, no, you went to the intermodal station, the train waits 10 minutes there and then it returns and you have not figured out that. So it means that sometimes you can do these kind of things. So the same for the node Q, but this here is the capacity of moving from the node, from one intersection P to another intersection Q without getting lost. If there is only one street, of course, this number here could be very small because these numbers could be very small and this number could be very large. But if you have that there are many clickishness around this node and a large clickishness around this node and a poor connectivity between the two, this distance would be very large. So it's telling you how far apart are two nodes in a network in terms of their communicability. And it is a distance. Okay, so now I will just go quickly here because this is just a mathematical part, but you can transform this into the length of path. Okay, so in a network, you cannot do anything outside nodes and edges. So then we can transform our network into a new network, somebody is sleeping, into a new network in which the weights are these communicability distances. So then it means that for different values of beta here, I can have different routes to move between the same pair of nodes. So it is easy to prove that the shortest path is a particular case of the shortest communicability path when this parameter beta here tends to 0. And here you can see for beta equal to 0.1, you recover the shortest path. So we have a measure which is Euclidean distance and that generalize the shortest path distance. So shortest path is just a particular case of this distance, but this distance try, as you will see, to avoid the hubs in the network. So this is just the shortest path, and as you would expect, the shortest path contains several of the hubs of the network, and this is the shortest communicability path, which is longer because it's not the shortest path, but avoid the hubs of the network. So now we have just to use our data and see what happens. So we go to IFISC. Here we know already that we're more people going by the shortest path than by the geographic one. But now this is telling you that people are not using the shortest path. People are using, in a large percentage, this longer path, like if they were diffusive particles, than going by the shortest path. Okay, so my first reaction was, this is wrong. Just repeat the calculation. So the guy repeat the calculation. So it returned and say, no, you are confusing the names of the path. So this is wrong. So go back, and then the results were the same. And then I say, no, okay, so believe me, my feeling was, okay, these people are mad. In Isfahan, I don't know this, you know, how the city is. Okay, so, and then I say to the guy, okay, just look for more data. Look for more data, other cities around the world. Anaheim, California, Winnipeg, Barcelona, and Isfahan. In all the cities that we analyze, it's very difficult to find this kind of data. We have the same. In Anaheim, this is the same, but we have normalized it to 1 in order to compare the different cities. In Anaheim, 35% more people go by the shortest communicability path than by the shortest path. In Winnipeg, in Barcelona, I remember it's 20%, and here I think it's 25%. So these are the numbers I remember. So people prefer to go by a longer path that avoid the hubs, that avoid these intersections. So, of course, when you say this to somebody and say, okay, so this is like a diffusive motion, because no, I am not a diffusive particle. I know, you know, every day I go to my work using this street and blah, 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 blah. Okay, but this is a collective phenomena. And fortunately, these two guys, one is a geographer and the other is an experimental psychologist, they do interview of thousands of people, what kind of algorithm you use to go to work. And somebody say, I use the longest leg first. Somebody say, I use the shortest legs first. I say, I go by the route that I take the fewest turns. I don't like to turn my car. Somebody, the fewest lights or stop signs. And then you have 24 of these. What happens, my friend, if you take 1 million particles, assign randomly and independently any of these algorithms of movement in the network and put all of them to move? What do you see? Random motion. Chan chan. This is what we get. And of course, we didn't get the medal from the mayor of Isfahan, but it was a very nice result. So you can do more things. So you can try to tune what is the value of beta and try to interpret this beta and blah blah blah. But I will skip this. So let's go down in the scale, and I think because of the time that should be the last example. And this is to introduce you something in which some of my students, I think the two of my students are working somehow now. But this is about the following problem. Unfortunately, a very good friend of mine passed away after being detected a glioma, which is a tumor in the brain. And this tumor is the one that is more frequent with age, and is also, I mean, these are only tumors in the brain, okay? So it is the most frequent of all the tumors in the brain, particularly when you are getting older. And also it has a very large mortality, so no more than 14 months since you are diagnosed. So what is the problem here? The problem here is diagnosing. So typically, and then you can, if you are interested, this is a very, very good paper about this. Typically, if you take the pathology, well, if you take a biopsy from the tumor, it's very easy to distinguish whether this tissue is healthy or is unhealthy. But unhealthy could be inflamed or it could be a glioma. And it's very difficult to distinguish between the two. So in many occasions, according to this paper written by physicians, what happens is that you are treated like if you had the tumor. So it means chemotherapy, radiation, and what you had was inflammation, and this enworsens your state. So the most sophisticated techniques like a magnetic resonance imaging, in many cases don't solve the problem, and only PET, so positron emission tomography, is the only one that can differentiate between the two cases, but in general, it's very, very difficult. So what I did is the following. So I contacted this group of people on bioinformatics in the States, and they have collected information in the form of tissues from pathology examinations of 30 cases of people that were known to have glioma, because these people has unfortunately died, and they took and see the tumors. People with inflamed brain, 30 cases, and healthy, 30 cases. So here, what you see here, these dots are the nuclei of the cells. And then by proximity, you can create a network. So the network is just the cells nuclei are the nodes, and they are connected if they are at a given radius inside one particular circle of a given radius. So you can play with this radius in order to guarantee, for instance, more connectivity, less connectivity, etc. So it's even by simple seeing, you can say, okay, these are all healthy cases and these are not. That's almost trivial case. But now differentiating these two things has been one of the most difficult things I have done in my life. So every time I introduce a new mathematical characterization of a network, I try with this data set, fail. I try it again, fail. I try it again, fail. Then one day I say, okay, if this is a tumor, it has to eat. It has to gain food from elsewhere. And this basically in this environment, cellular environment, is diffusion again. So let's try, and this is the problem that we have, considering different kind of diffusive process of this simple type. This is just the diffusive constant. This could be different kind of Laplacian operators, as you will see here, in order to try to distinguish between these three different cases. And you can figure out more. But this is normal diffusion. So what it means normal diffusion is that the particle, whatever is the particle is here, can hop just to the nearest neighbor. From here, can hop to another nearest neighbor, and so forth, completing just a walk, because it can do backtracking, but just one step by one step. But it could be some kind of anomalous diffusion. But this anomalous diffusion, and this is something that is completely new in this work, can be of two different kinds. So it can be like if you are driving and then you pass 3 or 4 intersections without stopping. So here, every time that you arrive at an intersection, you have the L in your car, so you stop. Okay, you stop at one intersection, you stop at one intersection, you stop at one intersection. Here, you travel 3 intersections without stopping, and then you stop here, and then you can travel 1 or 2 or 3 or 10. Okay, but then there is this weird type of anomalous diffusion, in which the diffusive particle disappears. If you have studied quantum mechanics, you can immediately relate to the annihilation and creation operators. So it disappears from one particular node and appears in the other particular node. It's not crossing by anything which is in the middle. How it can do that? Well, we already know that there are particles like exosomes, which are like a taxi, which are inside our cells, and they are in healthy people, but also in many kind of disease, and they transport proteins, pieces of DNA, etc. And what they do is they go out from this cell, it go to the blood, and then it can go to another cell. So then we can have these 3 different type of diffusion, and now the problem is, okay, for the normal diffusion, I can simply put there the normal Laplacian. What happened for this type of diffusion? I need some kind of modified type of Laplacian. So in 2012, I make a generalization of the Laplacian, and I will express this in terms of operator here, but I will give you a flavor in terms of matrices. So now I am producing here the LD, which are called D-path Laplacians, in which exactly the same as we have seen before, I take the function evaluated at the corresponding nodes minus the function evaluated at the node W, but this node W is at a shortest path distance D from the node V. If D is equal to 1, I recover the normal Laplacian. But if D is equal to 2, it means that the particle can hop 2 nearest neighbors away. If D is equal to 3, it can hop 3 nearest neighbors away. Okay, so now you can have a generalized type of degree. The D degree could be the number of D nearest neighbors that the node has. So the number of nodes which are at distance 2, if D is 2, the number of nodes which are at distance 3, etc., etc. So I have exactly the same representation of the Laplacian, but it's better one example, okay? So this is the normal Laplacian, which is now L1. Now L2 could be 1 is at distance 2 from 3, so there is -1. And 1 is at distance 2 from 5, so there is -1. It's not at distance 2, neither of 2 nor of 4. So then there are zeros here. And I take the sum of these with the change sign, and then I have the degree here. And then you complete this matrix, and the same for length 3. So if you do a transformation of this Laplacian, and there are different type of transformation, but this is the most convenient one, you say here that the hop between one particle and a node decays as the power law with the distance. So the probability that the particle goes from 0 to 1 or from 0 to 2 and so forth will decay with the separation from the node 0 to the node 1, node 2, and so forth. So S is, of course, a parameter that gives you the strength of this long-range hop of the particle. So let us consider an infinite path graph. So in this particular case, what I take is just the real line, but just of the integers here. And then I take here the diffusion equation in which I replace the normal Laplacian by the Meyin transformed d-path Laplacian. And D here is just my diffusivity. I will take equal to 1. And now my problem is to solve this equation analytically and see whether there is a qualitative change or not in the dynamic which is new equation is produced. So this is the solution. The first thing is that the probability of finding the particle at the initial position x is not Gaussian anymore. If it is not Gaussian, it is not normal diffusion. Do you recognize this? This is the ugly stable distribution, okay? And then what happens is that if S is exactly between 1 and 3, we have that the full width of the half maximum is scaled in this way, and this is the distribution that we have, indicating that there is super diffusion in the dynamic taking place in this particular network. So by simply changing this Laplacian by the d-path Laplacian transformed with the Meyin transformation, when S is equal or is between 1 and 3, you have a qualitatively new type of process. If you do other transformation, well, we have taken Laplace transform, normal diffusion. It can be accelerated or decelerated, but normal diffusion. If you take S equal to 4, normal diffusion. So it's only a process in one dimension. When you move to 2 dimension, you have here between 2 and 4. So it depends S of the dimensionality of the problem as usual. But then what is important is that you have this super diffusive process. So, okay, I will skip this. So almost not. The same year I published that paper, I forget, sorry, the reference here, Riascos and Mateos published this paper in which they suggest to consider long-range interactions by taking what they call the fractional Laplacian. So the Laplacian is a positive semi-definite operator, so it has roots that always exist and they are unique. So then it means that you can take the roots of this, well, this is just writing this in the form of the Cauchy integral, but if you take the spectral decomposition of the Laplacian, this is the metric of eigenvectors, and this is the diagonal metric of eigenvalues, then for alpha between 0 and 1, you have that, you only have to take the roots of the corresponding eigenvalues. So they have not proved analytically that there is super diffusion, but there are qualitatively change in the process. So what we did is simply try to explore whether these two Laplacians are taking the same kind of process, taking different processes. If they are taking different processes, what kind of processes they are considering at the end. So suppose that we have this type of process in which you have to cross this border in order to arrive here. So then it means that if I put a barrier here, when the particle tries to go to the node, let's say 3, it will be confronted with this barrier. So the probability of hopping to here, even if it doesn't stop here, will decay. And how can I do this in a network? Well, I can put a loop here with a weight. If the particle tries to go from 1 to 3, when it arrives here, it starts looping here. So if this weight is too large, the particle will be entertaining looping there very much, and this probability would be almost equal to 0. Now, what happens if the particle do this annihilation creation, as I mentioned before? That is almost independent of this, because it's hopping just through the air, and it's not affected by this. So now what we do is simply to test this hypothesis for a simple graph like this, in which the weight is changed from 1 to 10,000 here. And then this is what happened to the transformed, main transformed D-path Laplacian. First, there is an effect of the shielding strength here, so the weight of the loop, but then it's stable, it's stabilized here, and there is no influence anymore of the barrier, of the length of the barrier that I have put. So this is the normal Laplacian. Of course, for the normal standard Laplacian, if I put a loop in here, it could be very much affected because it has to stop here, then it will be entertained moving around this loop, and then it hops there. But the strange thing is that this also happened for the fractional Laplacian. So in the case of the fractional Laplacian, you are accounting for long-range interaction, but this long-range interaction is in this way. So you are traveling across the network. So the chemists use two words for this. They call this through bonds and this through space. So you can travel, an electron can travel through the bonds of the molecule, or can travel like in DNA through the space. So now we have this differentiation between the two. Let's go to return to our problem. So we define here a distance, which is Euclidean distance again between the nodes. And now we try, well, I am showing here for 1/2, alpha equal to 1/2, but you can do this for different values of alpha between 0 and 1, and the results are more or less the same. So here you have the distance, normalized distance for normal diffusion, and the normalized distance for anomalous internal diffusion. And what you see is that these make no differentiation at all between the three classes. And here is what you have when you use the super diffusive Laplacian in the case of the Meiji transform. So all the healthy tissues are here, and then the inflamed and the glioma are also separated perfectly here. So then it means, so this is again the distance of the normal diffusion between the different points in the network, and the same for, I call here external, but in reality, as you can see here, this is a combination of internal and external type of anomalous diffusion. So then it means that apparently gliomas are differentiated from inflamed tissues due to the differentiation that they do in the normal diffusion, while the unhealthy are differentiated from the healthy by taking into account this type of anomalous diffusion. So there is a sort of trade-off between the normal diffusion and the anomalous diffusion that allows you to differentiate. So from the perspective of the clinics, differentiating these things, job done. So you are already in a classification. You can do it even better. So you can separate the group of glioma into two groups. And this apparently corresponds to some gliomas. There is a World Health Organization classification of gliomas into 4 classes. Class 1, 2, 3, and 4. 1 and 2 are slowly growing gliomas, and 3 and 4 are the terrible ones, are fast-growing gliomas. And apparently this is the separation that is done here. So, but all in all, the results point here to a relation between gliomas and the existence of certain kind of anomalous diffusion, mainly involving long-range external type of jobs. So I will stop here, but you can go down. I still have 20 minutes, but you are tired and I am tired. So here you can do things at the cellular scale. This is more common to see in the literature. In this particular case, what I proposed in 2006, and this was one of the first papers in this area, is can I recognize biologically important proteins only from the topological information of the network? I mean, this is the protein-protein interaction of yeast. You know yeast? The most important organism in the world. It produces beer. Now, this is a serious matter. So, these red dots are essential proteins. It means if you knock out this protein, you don't have beer because the cell dies. Okay, can we identify these red dots only from the connectivity? Of course, you can tell me if you put biological information, yeah, this is what people are doing now. But at the very beginning in 2006, the problem was, is really network theory telling us something, or is just like a boom? Okay, so this is what we did here, and we implemented an algorithm here. So this is already an interesting result. If you pick proteins at random and check whether they are or not essential, you are able to identify 20%. But if you identify by degree, just by the number of connections, you are able to identify more than double of essential proteins than by random. So this is already an improvement. Remember that the guys which are in the wet lab, the biologists, they have to do a lot of experiments that cost a lot of money and a lot of time just to test whether a protein is or is not essential. So it means that you have to produce a mutation in the gene that produces the protein, then inject this gene modified into the cell, and then wait for seeing the result. So 80% of the time here, the guy is losing his time, and here only 60% of the time is losing it. But you can do it better if you take into account extra information. And this extra information came again from algebraic network theory by taking into account here the exponential of the adjacency metric. So if you take the II entries of the exponential of the adjacency metric, what you are doing is simply that you are counting, well, this is trivial, well, this is just in case that there are self-loops, but you are counting the degree, you are counting the number of triangles, higher order subgraph, but you are given weights in decreasing order here. So the degree has a weight bigger than A3 and A. So these are triangles, triangles more than squares, and so forth. And this is coming naturally from the Taylor series expansion of the exponential of the adjacency metric. So if you do it in this way, you improve from 46% to 60%. But now, can you do it even better? And the answer is yes. Okay, so you already showed in the first talk about bipartite networks. And mathematicians were studying bipartite networks for hundreds of years. Okay, and for a mathematician, a network was bipartite or not bipartite, black or white. But now take a bipartite network. Okay, so you have a set of vertices here and a set of vertices here. And there are connections between them, but no connection inside any of the two subsets. But now connect only one of these. The mathematician of the 20th century say, I am not interested in this because this is not bipartite. But the network scientists say, how much bipartivity is still remaining in that particular structure? How can we quantify? The first people that do this was Peter Holme in 2003 and I in 2004. And then the idea of Peter Holme was very clever. It was, okay, let me count the number of edges that I have to remove, divided, you know, the physicists call this the frustration of the system, but he felt frustrated because the problem is NP complete. You have first to do the drawing of the network into a bipartite structure, and this is NP complete. So then it means that you can use simple algebraic expressions in order to quantify how much bipartivity not only the whole network has, but also one particular node has. And then here is one example. So if you have this network I was telling you, in which I put this red line here, so the bipartivity of this node is affected. This index goes between 0 and 1, 1 for bipartite, as you can see here, and 0 for a complete network of infinite number of nodes. Now, this is bipartite, I destroy bipartivity, and the bipartivity of this node dropped to 0.93. Now, if I, instead of here, put the edge here, I am frustrating this triangle, and then it means that the bipartivity dropped more. If I put here, of course, it drops even more. If I put more edges, it drops more. And then when you arrive at the complete graph, you are converging almost to 0. So now you have a way to quantify how much bipartivity a non-bipartite network has. And if you do this for the nodes of the protein-protein interaction network, you are able to classify correctly almost 80% of the essential proteins. And this was in the cover of the journal Proteomics in 2006, because it was the first time that somebody said, okay, there is information about biology that can be obtained only from the topology of the network. And okay, so this is the final atomic scale. And in this particular type, what you do is that you can represent the structure of a protein as a network. How? Well, you can consider that every amino acid is one node. And two amino acids or two nodes are connected if the corresponding amino acids are at less than 7 angstroms of separation. They are physically interacting with each other. So see that even that this is a topological object and not a three-dimensional one, you still preserve certain information about the secondary structure of the protein. See that the coloring is the same in order for you to see this similarity. Well, all of you are tired of listening about SARS-CoV-2, and during the pandemic, I was involved in a national commission for the study of the virus. So I selected not to study the epidemiology, in which there were many groups working, but to try to understand how to kill the virus. Okay, and then the idea was at the beginning there were a few of the proteins that were already identified, and then it was identified that the virus, like many of the virus in this type, has a protease. A protease is like a digestive protein for the virus. So it is the one in charge of, once the two super proteins are produced by the RNA, it is in charge of cutting it into all the 20-something proteins that the virus has. And then what we did is to try to understand how an affection to one particular position of this protein can be affecting the functionality of this protease. So in other words, how can we design a drug that kills the virus by acting over the protease? And then what we did is, again, by using network theory, try to characterize by using the common measures that we have, the efficiency of transmitting information of the protease. And then what we see is that this is the SARS-CoV-1 of 2002, 2003, and this was the SARS-CoV-2. And then it was very disappointing, the news that we were receiving, because the similarity of the DNA, of the RNA, of the genomes of the two viruses was very high. And if you superpose the two proteases, the difference, the root mean square displacement of the superposition was very small. So the two proteases were almost the same. So it means that, for instance, the efficiency of this new virus, according to this, remember G is just the exponential of the adjacency metric, was only 18%. So it was not very convincing. So we were trying to understand what was happening here, and we produced more different kind of measures that were able to quantify that the new virus was almost 2,000 more efficient than the previous one in transmitting information at long range distance. So the short range distance transmission of information between the two proteases was almost the same, only 20% more in the new virus than in the previous one. But when you go for the transmission of information at long distances, then the new virus is almost 2,000% more efficient than the previous one. So this allows us to study how a drug connecting to this particular binding site was affecting this protease. And fortunately, relatively recently, a new drug that attacks exactly the same binding site of the protease as proposed in the paper has been commercialized by Pfizer and has been in the press with the name of Nirmatrelvir, whatever. So thank you very much. I still have 10 minutes, so thank you for your attention.